Hello students, let's solve the next question. The question is very simple. Calculate the thickness of a half wave plate from the following data. The refractive index for the extraordinary ray is 1.54. Refractive index for ordinary ray is 1.55 and the light being used is of lambda 600 nanometers, right? So what all is given? Refractive index for extraordinary ray. Observe the terminology that I am using. I am not saying refractive index of, I am saying refractive index for. Any is this. For ordinary ray it is 1.55 and wavelength used is 600 nanometer. That is 600 into 10 to the minus 9 meters. Okay. Now what is the concept being used here is that of a half wave plate. What is a half wave plate? It is a small device which is made up of birefringent materials. Birefringent materials are those materials that split a light ray into two rays. That is an ordinary ray as well as an extraordinary ray. Like in normal glass plate, what happens is it undergoes just refraction and it goes like this, right? Whereas in case of a birefringent material, if a light ray is incident like that, the wavefronts, no matter what kind of wavefront those are, when a light ray is incident on a birefringent material, it splits up into two rays, that ordinary ray as well as an extraordinary ray. Okay, there are different characteristics of ordinary ray and extraordinary ray. Now, the half wave plate is such a material whose thickness is such that the path difference between the ordinary ray and extraordinary ray will be lambda divided by 2. The path difference between ordinary ray and extraordinary ray is lambda by 2. That is, a birefringent material divides a light wave into two components. The path difference between those two components is lambda by 2, or the phase difference between those two components is pi. So that way the formula for this can be written as refractive index for ordinary ray minus refractive index for extraordinary ray multiplied by the thickness of this. Thickness is nothing but this one. It is equal to lambda divided by 2. Now, why am I calling this as refractive index for every time? Is because there is a particular axis along which we cannot see that these two things are splitting like this. Okay, they won't split. Ordinary ray and extraordinary ray both travel with the same speed along that axis. Okay, apart from that axis, which is called as optic axis, in all other directions, the refractive indices for that ray will be different. Okay, for velocity of extraordinary ray is greater than velocity of ordinary ray in case of negative crystals. Velocity of ordinary ray is greater than velocity of extraordinary ray in case of positive type of crystals. Okay, these theory concepts apart, let's try to solve this problem. Now what are we supposed to find out? T, right? So that is lambda divided by 2 into NO minus NE. That is lambda will be 600 into 10 to the power of minus 9 divided by 2 times 1.55 minus 1.54. So if you solve this, you will get 3 into 10 to the power of minus 5 meters. This is the thickness of half wave plate, so that it introduces a path difference of lambda by 2 between the two components, or a phase difference of pi between the two components. So the thickness is 3 into 10 to the minus 5 meters, or you can also write it as 30 micrometers, right? But this answer will be sufficient, no worries.